Hello, and welcome to Echoes of the Forgotten Earth, a place where curiosity settles in and science takes its time. Whether you're easing into the night or letting your thoughts drift before sleep, I'm glad you made it. This evening, let's follow a question. Not one with neat answers or sharp corners, but one that nudges us to rethink the ground beneath our feet. What if Earth were designed? I don't mean design like something pulled off a shelf or assembled like a flat-pack bookcase, though the thought of tiny cosmic tools is undeniably charming. I mean the broader notion. What if Earth wasn't merely the product of happenstance and unguided physics, but was shaped deliberately, methodically, by some force or process? However you imagine that, an intelligent maker, a sophisticated simulation, a vast natural algorithm, or something else entirely, is up to you. The point is, we're not here to argue. We're here to explore. No shouting, just quiet questions. And we're not in a hurry. That isn't our rhythm. Instead, we'll take an unhurried walk across this landscape of ideas, noticing the small textures and the sweeping patterns. And maybe, as we meander, we'll find that the act of asking opens new ways of seeing. Ways that matter as much as any answer, perhaps even more. Let's begin close to home, not with equations or doctrines, but with the ordinary act of looking around. Think about a typical day. Morning light spills through your window, not too hot, not too cold. You inhale air your body is exquisitely suited to use. You feel thirsty, and as if on cue, water clear, tasteless, essential awaits. Maybe you step outside. Plants, animals, sky, temperature, gravity. Everything seems set just right, not only to allow life, but to make it comfortable. It's easy to let that fade into the background. Most of us do. But beneath that ease is a pause-worthy thought. Is this all coincidence? Could it be? Or is the world arranged like puzzle pieces that fit a little too precisely? Science, of course, has offered a rich, carefully developed story. There's no shortage of knowledge about the early solar system, the formation of planets, chemical evolution, and the rest. We've built models, gathered data, and traced timelines across billions of years. It's a sturdy framework. And yet within that framework sit details that make people hesitate, things that, frankly, feel suspiciously convenient. Earth orbits a notably steady star, and does so within the so-called habitable zone, where liquid water can persist pretty central for the kind of life we know. Fortunate, yes, but it doesn't stop there. The planet's tilt brings seasons. Its spin tempers extreme temperature swings. The moon's size influences tides and helps steady that tilt. Our magnetic field shields us from the sun's charged particles, the atmospheric mix, the ratio of land to ocean. You can keep listing them. Each of these could have been radically different. If they were, the life we recognize might never have appeared. Some fold this into what's called the anthropic principle. Naturally, the universe looks life-friendly to us. We're here to observe it. If it weren't hospitable, we wouldn't be around to ask. It's tidy, in a way. But the wondering doesn't quite stop. Is we're here, so it worked? Enough? Or are we sidestepping something deeper? None of this proves design. That matters to say plainly. Patterns don't prove purpose, but they can point toward it, or at least make it worth considering. So we'll study those patterns not as believers or skeptics, but as wanderers. We'll move among clues and coincidences, through physics and philosophy, math and metaphor, slowly, without rushing toward a single verdict. Because whether Earth was designed or not, it often behaves as though it were. That's not a declaration. It's an observation, an invitation to ask, if it were designed, what would be different? What would remain just the same? To explore this, we'll have to range both wide and deep. We'll talk planetary physics, yes, and biology and chemistry. But we'll also talk about perception and story, about why humans are drawn to the notion of a world made with intention. Some of that comes from religion, certainly, but not all. The urge to look at the sky and feel it means something is older than any scripture or sanctuary. It may be built into us. Consider symmetry. We're attracted to it. Faces, flowers, shells, galaxies. Our brains brighten when we see it. It feels right. That preference doesn't prove anything, but it gives us a place to start. Why would a universe born of randomness keep producing order? Why does our sense of beauty so often align with what proves efficient, functional, and mathematically elegant? Even if you begin with a strictly scientific outlook, you quickly find yourself swimming in questions that sound philosophical. The more we learn about biology, for instance, the more we see how tightly tuned many systems are. Protein folding, the information architecture of DNA, the communication among cells, so precise, so interdependent, so startlingly efficient. Not flawless evolution is messy, and our bodies carry quirks and leftovers, but it works, and it works astonishingly well, sometimes in ways that resemble what we casually call design. Design is a loaded word. It often conjures a conscious agent drafting blueprints or nudging molecules, but it doesn't have to mean that. It can also mean structure, direction, pattern arising not from pure chance, but from a bias towards certain outcomes. Even if we don't know the source of that bias, the idea that Earth is designed doesn't require a specific designer. It might point to a universe governed by deep logic that happens to yield life-friendly results, or something else altogether. There's also the selection idea. Perhaps Earth wasn't constructed from scratch. It was chosen. Out of many possible worlds, this one supported life. And so, here we are. But that sparks another question. How many possible Earths exist? Are we the lucky one in a trillion? Or is the cosmos brimming with other worlds like ours, each with its own brand of stability and strange beauty? We don't know yet. As we catalog exoplanets thousands and counting, we're starting to map how rare or common Earth-like conditions might be. So far, nothing quite mirrors what we have. We've found worlds that are too hot, too cold, too massive, too compact, too irradiated, or too young. Some lack atmospheres. Some have far too much gas. Others circle stars that flare unpredictably. The more we look, the clearer it seems that Earth is unusual. Not impossible. Not unique. But not typical either. Then again, with a universe this vast, average can be slippery. Maybe the rarity of Earth-like setups is exactly what randomness would produce. Or maybe it hints at something else. Either way, it keeps the question alive. There's also timing. Not just where we are, but when. Life needed the right ingredients, but also the right sequence. Yes, a stable planet. But also billions of years of relatively calm cosmic weather. Not too many asteroid hits. Not too many solar tantrums. A moon to help steady the tilt. Tectonics to recycle carbon. An atmosphere that slowly evolved in the ways life required. The order of operations mattered. Not impossible, just another piece in a growing puzzle. People explain this in different ways. Some call it providence, others luck, others inevitability given enough time and space. Yet the notion that Earth might be intentionally arranged either directly or via deep structures in nature's laws stays compelling, not because we can prove it, but because it resonates with the lived experience. We are builders, we plan, we imagine outcomes before they happen. When we encounter a world that seems tailored just so, it's natural to wonder whether someone or something meant it. Still, caution helps. Patterns can emerge from chaos. Perception can mislead. Feeling that something is designed doesn't make it so. Unlikeliness doesn't imply intention, but the reverse holds too. Explaining how something happened doesn't mean we've said why, or that there isn't a deeper structure we haven't yet glimpsed. So we're not here to dethrone science or enshrine belief. We're here to keep a space where both can ask the same question from different angles. What if Earth were designed? What would change? What would remain? And what, if anything, would that mean for how we live, how we see one another, and how we move ahead? As we continue, we'll turn to specific features that often surface in this conversation. The orbital sweet spot, the moon's peculiar influence, the atmospheric balance, the oddities of DNA, the many systems that had to align for intelligence to emerge. Each opens its own cluster of questions, not just scientific ones, but questions about what we expect reality to be. When we ask whether Earth was designed, we're not merely talking planets and physics. We're brushing against something more intimate. Beneath the science and speculation, the question is personal. It's about our place. Is life a fortunate accident that happened to work, or something more deliberate? Do we see the world as a chain of coincidences, or as part of a reality meant to be as it is? That's why the idea feels different from asking how volcanoes form or why seasons shift. Those are interesting but not tender. Asking whether Earth might have been made on purpose steps into a much older conversation, one that began long before telescopes or textbooks, when the first people looked up and wondered what it was all for. You find it in philosophy, religion, and myth stories of Earth, shaped by hands or spirits or voices that spoke the world into being. While those stories diverge in their details, they share something vital. They show a human instinct, the urge to link what is to what it means, to turn facts into purpose. That instinct is not something to discard lightly. It's easy to say, science tells us how, and meaning tells us why, as if the two live in separate rooms. But the boundary isn't always neat. The deeper we understand how the universe works, the more we notice moments where structure and outcome seem to meet in ways that feel there's no better word guided. Consider carbon. Life here is built around that one element. Carbon forms the backbone of DNA and proteins, the intricate chemistry that powers cells. It's astonishingly versatile. It bonds readily. It forms long chains. It builds stable molecules that can store information and create structure. Without it, life as we know it wouldn't function. Look at how stars forge elements and you find that carbon arises under a very narrow set of conditions. If the physics of fusion were even slightly different, stronger, or weaker, the universe might brim with hydrogen and helium but lack carbon. No carbon, no life, no us. That kind of specificity makes people pause, not because it proves anything, but because it reveals how precise things had to be. And the deeper we probe the laws of physics, the more we find many values, masses, charges, the strength of forces, gravity, have to sit inside tight ranges for complex matter to exist at all, let alone life. Not just biology, but stars, planets, chemistry. We sometimes call this fine-tuning. It raises a quiet question behind much of modern science. Why these numbers? Why this version of reality? There are responses. One is the multiverse. Maybe countless universes exist, each with its own constants. And we happen to inhabit one where everything lines up. Perhaps. But we don't yet have direct evidence for other universes. And even if we did, that still wouldn't say why ours exists as it does. It simply moves the question one notch back. Another idea is that these values weren't chosen at all. They emerge from a deeper structure we've yet to uncover. That, too, is a kind of mystery. Either way, we're staring at a reality where many things had to be just so. And they are. Inevitably, you reach the deeper formulation of the question. Not merely, why is Earth like this? But why is anything like this? Why do physical laws exist? Why should there be a universe with rules, patterns, and matter? Why should there be something rather than nothing? No telescope can answer that. Yet we keep circling back. Science, to be clear, doesn't require purpose to function. You can study gravity without believing it was devised. You can parse DNA without asking who wrote it. Science doesn't forbid those questions. It simply doesn't depend on them. For some, that leaves a middle ground, a place where you can follow evidence and still allow that something might be happening beyond what we can measure. In that space, design enters not as a substitute for science, but as a lens. It doesn't say we should stop asking once we see fine-tuning. It says the fine-tuning itself is worth our attention. And maybe, only maybe, it hints at something deeper. Of course, people disagree on what that something might be. Some picture a conscious designer, a god, an architect, a being with intentions. Others imagine an intrinsic intelligence in the universe, not a person, but a process that tends toward order, beauty, or complexity. Still others see design as projection, a story-seeking species imposing patterns on the world. In all these views, the question remains, even as the answers diverge. It sits quietly behind our work. Every discovery, every satellite image, every equation or theory is framed by the curious fact that we are here looking, that there is something to look at, and that it behaves in ways we can understand. Pause on that. Not just that the world exists, but that it's intelligible, that we can measure, predict, and explain it. That a brain evolved from ancient nervous systems built to hunt and survive can now model galaxies, build computers, and ask whether the universe has a purpose. Why should the mind of a species on a small rock in a quiet corner of a galaxy grasp the rules of space and time? It proves nothing, but it's odd. It makes you wonder whether our capacity to understand is itself part of a larger pattern, whether the universe is not only structured, but structured to invite understanding. Not a claim, just a thought. In the end, these questions need not threaten. They don't diminish science. If anything, they show how science can carry us right to the edge of mystery and keep going. Not every question must be answered to matter. Sometimes holding the question is enough, and this possibility that the world was built, arranged, or shaped is among our oldest and also among our most modern, because now we have tools to look more closely than ever at matter's building blocks, at nature's forces, at life's dynamics. As we do, the question deepens. Not because we're running out of explanations, but because the explanations themselves are so intricate, so exact, so delicately balanced that they make you pause. They make you ask, is this simply what happened to work, or what was meant to happen? We can't answer fully. Not yet. Maybe not ever. But we can keep asking. We can follow structure and order and logic, not to win an argument, but to understand, and perhaps draw a little nearer to whatever lies at the heart of it all. When we shift our gaze to Earth itself, not just its cosmic address, but its surfaces, systems, and the everyday substances beneath our feet patterns appear. Some geological, some chemical, some mathematical, some architectural. The closer we look, the more those patterns can feel curiously intentional. It begins with fundamentals. Earth's crust is broken into plates. Those plates float atop a warmer, softer mantle, drifting over long spans of time. That motion builds mountains, sparks earthquakes, drives volcanoes, even opens oceans. Without plate tectonics, Earth's surface might be flat and static. Erosion would grind it down. Nutrients wouldn't cycle. Life as we know it might never have flourished. Plate movement also helps regulate carbon. Volcanoes vent CO2. Mountain weathering draws CO2 back down. That balance shapes climate, which in turn shapes the biosphere. Science has mapped this in great detail, but zooming out, it's hard not to notice how many ways the system could have failed. Earth didn't just need a solid crust, it needed one that cracked, floated, and moved. If the crust were thicker, or the mantle stiffer, the plates might stall. Too active, and the surface would be constantly remade, leaving no time for life to stabilize. Somehow, Earth landed in the middle. Not too quiet, not too wild. The middle shows up elsewhere. Soil, for example, blends minerals, organic matter, water, and air. But the proportions must be right. Too sandy and water runs straight through. Too clay heavy and roots can't breathe. The best soils, those that feed forests, crops, and entire ecosystems, strike an artful balance. That balance can vary by region, but it always falls within a narrow band. Plants adapt to those conditions, or perhaps the conditions shape the plants. That dance appears everywhere. Coevolution. Not just plants and soil, but insects and blossoms, fungi and trees, bacteria and animal systems that don't merely function, but function together. Each part shaped by the presence of the others. Sometimes the fit is so precise it feels more like assembly than adaptation. Consider a seed. It contains the instructions, the stored energy, the architecture. It waits in darkness, listening for moisture, temperature, light. When the cues align, it transforms. Roots press downward, shoots reach upward. We can describe it biologically, but the timing, sensitivity, and precision are striking. Even seed shapes the ways they stick, drift, sink, or float seem optimized. Not perfect, but impressively effective. It's easy to attribute all of this to natural selection. Traits that worked persisted, those that didn't faded. But selection works with what exists. It doesn't craft from nothing. It repurposes, trims, and refines. So the starting materials matter. Look at those materials. The elements of life. Carbon, nitrogen, oxygen, hydrogen. They aren't only common, they are strangely versatile. They bond readily. They store energy well. They assemble into the kinds of molecules that loop, twist, and replicate. Of course, that's chemistry. But chemistry follows rules. And the rules in our universe seem to lean toward complexity. Not that complexity is inevitable, but once it starts, it has room to grow. Earth, for whatever reason, seems to have given it a head start. Take water. It isn't exotic, but it has peculiar traits. It expands when it freezes, so ice floats, allowing life to persist beneath frozen surfaces. It has high specific heat, buffering temperature swings. It dissolves more substances than nearly any liquid, making it an ideal medium for reactions. These properties are exquisitely life-friendly, and they all trace back to the angle of two hydrogens bonded to an oxygen. Nudge that angle and water behaves very differently, and so would everything that depends on it. Then there are fractals patterns that repeat across scales. You see them in rivers, mountains, coastlines, branches, blood vessels. They're not just beautiful, they're efficient. They distribute resources across space with minimal material. Trees feed leaves from roots through fractal networks. Our lungs do the same with air. These forms aren't arbitrary. They follow mathematical rules that reappear independently in disparate systems. Some call it convergence. Others glimpse something more deliberate. You also see the Fibonacci pattern, the spiral in shells, pine cones, sunflowers, even galaxies. Not universal but common, especially where growth is involved. It enables efficient packing and expansion. There's a mathematical reason, yes. But the fact that math threads through biology at all is worth noticing. Organisms shaped by blind processes over eons often align with principles we find elegant or logical. It raises a curious question. Does the universe obey math because it must? Or does math describe it so well because both spring from the same source? That's not only philosophy, it matters for how we read structure. If life arises from patterns and those patterns follow rules, where do the rules come from? Here the blueprint idea enters. Not blueprints as literal schematics, but as stable systems that yield consistent outcomes. Earth isn't random, and it isn't pure chaos. It's ordered, layered, functional. From soil chemistry to orbital dynamics, things behave in repeatable ways. Science relies on that regularity. But that same regularity makes some wonder whether it points beyond itself. Patterns can emerge from chaos models show it. Yet those patterns usually need specific initial conditions. Tweak them, and the outcome shifts. Which makes you wonder, what were the initial conditions here? Why these laws? Why this structure? Why a world where minerals grow crystals, plants sense light, and animals evolve eyes? None of this demands anything supernatural. But the more closely we examine Earth's structure, its soil, its systems, its cycles, the more the question comes back. Could this have been arranged? Not by magic, but by a process we don't yet understand. One where design isn't a choice so much as a principle, a natural drift toward life-supporting systems. We don't have to decide that now. We're not here to answer so much as to notice. And what we notice is that Earth is not a haphazard heap. It's a deeply interconnected whole, full of rules, balances, and alignments that lean towards stability, growth, and resilience. Not perfect. Far from it. But it works, and in ways that feel oddly tuned. When people ask why life thrives on Earth but not on Mars or Venus, they often mention the Goldilocks zone, the orbital band around a star where temperatures are just right for liquid water. Since water seems essential for known life, a planet in that comfortable band stands a chance. Earth sits near the middle, close enough to avoid freezing, far enough to avoid boiling. Our sun is steady and long-lived, gifting Earth billions of years to develop complex ecosystems. It's tempting to hear that and feel that the universe threw a dart and nailed the bullseye. But, as usual, the closer you look, the more nuanced it becomes. The habitable zone isn't fixed. It depends on a star's size and brightness. Dimmer stars draw the zone inward, but small stars often flare, blasting radiation that can strip atmospheres. Hotter stars push the zone outward, but they burn fast, leaving less time for life to unfold. Our sun is unglamorous and average in the best way. Stable, bright, long-lasting. Maybe not the only type that can host life, but certainly among the friendlier options. Then there's orbit. Earth doesn't merely sit at the right distance, it stays there. Our path is nearly circular, so the solar energy we receive doesn't swing wildly over a year. Some variation is helpful, that's how we get seasons. Too much variation, though, and climate would lurch between extremes. Our wobble is modest. Our tilt is lively enough to stir things without overturning them. Distance and orbit are just a start. A planet can sit in the zone and still be barren. Look at Mars. It lies near the outer edge and holds ice. It likely had flowing water long ago, but now it's dry, cold, and bathed in radiation. Its magnetic field collapsed. Its atmosphere bled away. No shield. No pressure, no warmth, no refuge. At the other end is Venus, just inside the inner edge. Similar in size and composition to Earth, but wrapped in a thick shroud of carbon dioxide, it underwent a runaway greenhouse effect. The surface is hot enough to melt lead. Clouds are laced with sulfuric acid. If Earth is a warm cup of tea, Venus is a kettle that never stops screaming. So Earth occupies a narrow window, not just in distance, but in how its systems mesh. The atmosphere traps enough heat, but not too much. Oxygen, nitrogen, and carbon dioxide sit in a life-friendly mix. Oceans temper climate. Weather redistributes heat. The greenhouse effect exists but hasn't sprinted away, at least. Not yet. It isn't a fragile balance so much as a dynamic one thing shift and compensate. Change one part, others respond. That adaptability helps stabilize the whole. Again, it didn't have to turn out like this. Small differences early on could have sent us down other paths. Rewind far enough and you reach the solar system's birth. The whirling cloud of dust and gas that formed the sun and planets. Where Earth ended up was shaped by gravity, collisions, and leftover debris. It might have formed farther out and frozen, or closer in and baked like Mercury. But it didn't. It formed here in the zone where water could stay liquid and life could take its time. Some call that chance a roll of the cosmic dice. Fair enough. Others look at the result. A planet with the right temperatures, chemistry, and history. And wonder whether the dice were loaded, not in a crooked way, but in a way that suggests direction. Maybe not intentional, but not indifferent either. Is the Goldilocks zone rare or routine? Many stars seem to host planets in that range. We've found thousands of exoplanets. Quite a few sit where water could flow. But we don't yet know if they have atmospheres, oceans, or magnetic shields. We don't know if their climates are steady or violent. We don't know their inner workings. And even if the ingredients are present, we don't know whether life ever had a chance. So Earth remains our clearest case study. The more we study it, the more fine-tuned it appears. Not in the sense of perfection, climate shifts, disaster strike, ecosystems falter, but overall, the balance holds. Life persists. Not just simple life, but complex reflective life that asks how this happened. Just right. Sounds simple. It isn't. It wraps hundreds of interacting systems, geology, weather, magnetism, chemistry, biology acting, in ways that sustain life's presence and continuity. It isn't only where Earth sits. It's everything that sitting there makes possible, that still may not prove anything. Perhaps it's a lucky outcome. Perhaps life is rare but not impossible, and Earth is one of the places where things aligned. That's the standard scientific reading. But there's also a quiet, persistent sense, not a conclusion. Just a feeling that the alignment reaches beyond odds, hinting at something deeper about how the universe works, or wants to work. If we assume design, what might it be steering toward? Life? Complexity? Balance a system that holds together long enough to become interesting? That doesn't make Earth a utopia, but it does put it in an unusually good position for something rare and intricate to unfold. Once we look past where Earth is and focus on what Earth is, the planet's structure becomes part of the story. Not only the surfaces we cross, but the entire arrangement from the iron heart at its center to the shape of its path through space. If Earth were meant to host life, you'd expect its structure to matter. And even if no deliberate purpose lies behind it, the way its parts fit together raises intriguing questions. Much of it starts at the center. Earth's core, mostly iron and nickel, has two layers: a solid inner core and a liquid outer core. Movement in the outer core powers our magnetic field, shielding the surface from solar and cosmic radiation. Without that field, charged particles would batter the planet, eroding the atmosphere, damaging DNA, and making life far harder, maybe impossible. That shield isn't just there. It's generated by a geodynamo. Earth's rotation stirs the liquid metal. Those flows generate electric currents. The currents produce the magnetic field. For this to work, several conditions must hold. You need the right materials. You need internal heat from radioactive decay and leftover energy from formation. You need sufficient size small worlds cooled too fast. And you need rotation, but not excessive rotation. Earth spins once every 24 hours, fast enough to keep the core churning, slow enough to avoid havoc at the surface. Change any of those, shrink the planet, slow the spin, reduce the metal content, and the magnetic engine could stall. That's what likely happened on Mars. It probably had a field early on, but cooled too quickly. The core's motion faded, the shield collapsed, and the atmosphere slowly slipped away. Above the core lies the mantle, creeping over deep time, driving plate tectonics. Those plates, as we noted earlier, are pivotal recycling minerals, sculpting continents, raising mountains, regulating carbon. They require heat and a delicate balance between stiffness and flow. If the mantle were too soft, the crust would shatter constantly, too rigid, and nothing would budge. Earth seems to have found the right settings, dynamic, not unstable. Over ages, continents drift, collide, break, and reform. That movement reshapes climate, creates new habitats, and isolates ecosystems, a key engine of biodiversity. It's part of why so many life forms evolved in distinct regions. Without that slow dance, the surface might be monotonous and stagnant. Even the crust matters. It's thin compared to the planet, just a handful of kilometers under oceans, thicker beneath continents, but it's the only layer where surface life resides. Its composition is rich in elements life needs: carbon, phosphorus, sulfur, calcium, potassium. Not all of those were present in the original mix. Many arrived during the late heavy bombardment, when asteroids and comets delivered water, organic molecules, and other essentials. That period could have gone very differently. Too many impacts, and the surface might never have cooled. Too few, and the pantry might have been bare. Instead, Earth seems to have received just enough a blend of rocky and icy visitors added to what was already here. Another moment where things didn't have to line up, but somehow did. Wrapping all of this is the atmosphere, a barrier and a support system in one. It keeps Earth warm, guards against small meteoroids, and carries the gases needed for breathing and photosynthesis. But it didn't begin that way. Earth's first skies were likely thick with carbon dioxide, methane, and ammonia, poisonous to modern animals, yet suitable for ancient microbes. Over time, photosynthetic life began releasing oxygen, gradually remaking the air into what we breathe today. That shift, the Great Oxygenation Event, could have tipped either direction. Oxygen is reactive. In high doses, it damages. But in the right proportion, it fuels complex metabolism, opening the door to multicellular life. The remarkable part is that Earth's systems didn't unravel under the stress of that transition. Feedback loops, some amplifying, some damping, kept conditions within certain bounds. The balance between carbon dioxide and oxygen is still shepherded by living systems. Forests, oceans, and soils sequester carbon. Volcanoes and respiration return gases to the air. The result isn't a perfect equilibrium so much as a long-horizon self-adjustment. In that sense, Earth's surface behaves less like a rigid machine and more like a living body, responsive, flexible, continually adapting. And then there is water. Its spread is uneven, but its impact is sweeping. Roughly 70% of the planet is cloaked in ocean, moderating temperature and circulating nutrients. Fresh water runs through rivers and lakes, hides in ice, and rests in aquifers. That blend sustains sea life and land life alike, all powered by a planetary choreography of evaporation, rain, and flow, governed by geography and sunlight. Even the planets tilt about 23.5 degrees shapes where the light falls, carving the seasons. The moon helps steady that tilt. Without the lunar ballast, Earth's axis could lurch chaotically, driving sudden climate swings. Instead, we get a dependable cadence that life has learned to follow. Migrations, hibernations, bloom times, each tuned to the angle of the sun and the arc of the year. Put these pieces together, and Earth stops looking like a simple rock in space and starts to resemble a layered organism. A world that generates its own magnetic shield, tempers its own climate, recycles its own resources, and hosts and sustains its own life. A planet that creates the conditions it needs and preserves them through feedback and flow. None of that proves more than what we can witness. But it opens a different lens. Rather than treating Earth as a fortunate bundle of traits, you begin to sense an inner logic, not one imposed from outside necessarily, but a logic that tends toward life-supporting outcomes. Whether that logic was baked in from the start, emerged over time, or belongs to some wider framework, that's the question we keep circling. For something that keeps us company night after night, the moon is a curious partner. It's unusually large compared to its planet, its gravity strong enough to tug at the oceans, and its influence on Earth's steadiness is more than incidental. It may be one of the main reasons life has persisted here for so long. At first glance, the moon seems like a natural byproduct of solar system formation, but the closer scientists looked, the less straightforward its presence became. The leading idea is the giant impact hypothesis. A Mars-sized body, often called Theia, likely slammed into the young Earth. The collision lofted vast amounts of material into orbit, which gathered and cooled into what became the moon. This helps explain why lunar material so closely matches Earth's outer layers, and why the moon settled into a relatively close, stable path. It also fits our broader models of how early worlds formed and jostled one another. But that story relies on a remarkably specific setup. The impactor had to be large enough to throw debris into orbit, not so large as to obliterate Earth. The strike had to be oblique rather than head-on. The ejected material had to clump instead of dispersing. And afterward, the new Earth-Moon system had to calm into a long-lived orbit. It's a tight target. Nudge the speed or the angle, and perhaps there's no moon at all, or a chaotic ring or a second body that eventually falls back. Instead, we ended up with one big moon, tidally locked, so it shows us the same face, circling at just the distance to matter without making a mess. Those effects matter a great deal. Most importantly, the moon helps steady Earth's axial tilt. Without that stabilizing mass, our axis could wander through large swings from near upright to severe angles upending climate patterns. Seasons might become erratic or vanish. Mild regions could freeze or roast, then swing back again. That kind of volatility would make long-term ecosystems far harder to sustain. The moon also drives tides. Tidal motion stirs nutrients along coasts, moderates temperatures in shallow seas, and may have contributed to life's beginnings by creating cycles of wetting and drying that favor certain reactions. The ocean's pulse doesn't just animate shorelines. It shapes weather, redraws coasts, and influences the behavior of countless species. There's timekeeping too. The moon's tug slows Earth's spin by tiny amounts. Billions of years ago, a day lasted roughly 6 hours. Tidal friction has stretched it to the 24-hour cycle we know. The process continues, imperceptible in a lifetime, but over ages it likely nudged the climate toward greater stability. And then, there is night itself. Not in a mystical sense, but a biological one. Many organisms key off the lunar cycle. Coral reefs release gametes in synchrony with moonlight. Some insects navigate by it. Predators and prey alike adjust their habits based on how bright the darkness is. The moon provides a reliable rhythm that many life forms have woven into their biology. What makes this more striking is that large moons around rocky planets seem uncommon. Mars has 2 misshapen, likely captured rocks. Mercury and Venus have none. In current formation models, big moons are not an automatic outcome. They're unusual. Yet Earth has one, and not just any, but one that seems tailored to its role. That's what keeps the question alive. Not because anyone imagines it was placed with tools and plans, but because the result, a stable, life-friendly world with a stabilizing satellite, is uncommon enough to notice. The moon's origin, orbit, and influences add another layer to how Earth ended up so specifically equipped. Some go further with speculative possibilities. Perhaps the moon slightly altered the paths of incoming impactors, marginally reducing catastrophic strikes. Perhaps its gravitational pull affected heat flow within Earth, subtly influencing the geodynamo that powers our magnetic field. These ideas are harder to test, but they underscore a growing sense that the moon is an active participant in Earth's story, not a passive ornament. Even now, the relationship changes. The moon drifts away at roughly 4 centimeters per year. On human scales, that's nothing. Over geologic time, it matters. In a few billion years, total solar eclipses. The precise fit of moon over sun will cease. The moon will appear too small to mask the solar disk. Like many features of Earth, this perfect alignment is part of a limited window, temporary, but long enough to shape what happens here. Most of the time, gravity slips by unnoticed. It's always there, always working, and almost always ignored until something falls, or you step on a scale or a cup tips and reminds you that invisible forces still have the final say. Yet in the business of building a planet and keeping everything on it in place, gravity is more than background. It's the structure beneath the structure. By physics standards, gravity isn't strong. Compared to electromagnetism or the nuclear forces, it's feeble. A small magnet can hoist a paperclip against the pull of an entire world. But what gravity lacks in punch, it makes up in reach. It never shuts off, never gets screened, and acts on everything with mass. That quiet persistence makes it a master organizer. Without gravity, Earth wouldn't be round. It wouldn't even be a planet. The material that became Earth would still drift in a wispy cloud, never compacting into anything solid. Worlds form because gravity slowly gathers dust and gas, compressing them until pressure and heat shape a dense sphere. The same pull separated Earth into layers, core, mantle, crust, not at random, but by density. Heavy elements like iron and nickel sank inward. Lighter materials rose. Gravity sorted the planet by weight, and that sorting still dictates how Earth functions. Gravity does more than sculpt the planet. It keeps the moon in its path, draws the oceans into tides, and locks Earth into a reliable orbit around the sun. Without it, the planet wouldn't just lose its shape, it would lose the framework that holds everything together. No orbit, no seasons, no buffer from the empty cold of space. Earth's orbit is worth a pause. Our path isn't arbitrary. It's a stable, nearly circular track born of balanced forces. The forward motion of Earth and the inward tug of the sun. Too fast, and we'd sail away. Too slow, and we'd spiral inward. As it is, speed and position cooperate to keep us in a near-perfect loop, a kind of falling that never finishes. That steadiness underpins long-term climate patterns and provides predictable cycles of seasons, daylight, and energy. Life learns rhythms, and those rhythms depend on gravity doing exactly what it does. The sun isn't the only body tugging on us. The moon raises bulges in the ocean's tides we feel at the shore. Even the solid Earth flexes slightly, a phenomenon called Earth tides. These subtle shifts add stress within the crust, and, over great spans of time, help shape tectonic activity. In that sense, gravity isn't merely holding the system together. It's guiding how it moves and evolves. Even Earth's axial tilt, the angle that gives us seasons, stays within limits partly because of gravitational interactions. Without those checks, the tilt could drift or swing wildly. Instead, the combined pulls of sun and moon keep it inside a narrow band. That's another way gravity fosters a predictable environment, not by freezing things in place, but by setting boundaries within which change can unfold. On smaller scales, gravity writes the landscape. It draws glaciers downhill, channels rain into watersheds, and over ages carves valleys, raises cliffs, and spreads plains. Trees feel it, too. Roots delve downward, stems lift upward, guided by tiny cellular sensors that read the direction of pull. These effects are easy to overlook because they're slow. Gravity doesn't flash or hum. Its influence is continuous, a quiet thread connecting the rotation of the core to the position of clouds. There's a human chapter to this as well. Our biology is tuned to Earth's pull. Bone strength, blood flow, balance. Each assumes a specific acceleration of roughly 9.8 meters per second squared. In low gravity, muscles atrophy, fluids redistribute, vision can change. Astronauts feel these shifts because their bodies are adapted to a force that suddenly isn't there. If Earth had a bit more mass, gravity would be stronger and our bodies might skew shorter or sturdier. With less, the air could be thinner or leak away entirely over time. Size and mass aren't just numbers. They're part of what makes surface life possible. The atmosphere clings. Water moves as it does. Animals grow to certain scales. Birds and insects fly with wings shaped by these exact conditions. Beyond Earth, gravity is still the chief architect. It binds galaxies, steers stars, and bends the paths of light from distant objects, an effect we use to detect things we can't see directly. That bending gravitational lensing is one of the clues that dark matter exists. We don't see gravity itself, but we feel its presence in everything that holds still, and in everything that moves with purpose. In a universe that often looks unruly, gravity is one of the few forces that gathers things into order, not with clockwork perfection, but with steady persistence. It doesn't solve every mystery, but it sets the stage on which other mysteries can play out. Without it, none of this would be here. Of all the substances in the cosmos, water might look like one of the simplest. 2 hydrogens and an oxygen. That's it. Yet it behaves in ways that make it far more than a mere compound. On Earth, water is everywhere. It fills the seas, drives the weather, shapes the land, and threads through every living cell. It's essential to life as we know it. And when you look closely at how it acts, and how rare that behavior is, it gets harder to treat water as a simple stroke of luck. Water has a handful of traits that are genuinely unusual. One of the biggest is its ability to exist as solid, liquid, and gas within the ordinary temperatures Earth provides. That isn't common. Many substances favor a single state or require extremes to switch. Water freezes, melts, and evaporates within a narrow band that aligns neatly with our climate. Those phase changes do real work. Evaporation soaks up heat, cooling what's beneath. Condensation gives that heat back, warming the air. This exchange redistributes energy around the globe, fuels storms and winds, and keeps climate from drifting too far in any one direction. Another standout is water's high specific heat, the capacity to absorb a lot of energy before its temperature shifts. Because of that, oceans and lakes act like thermal flywheels. They store heat in summer and release it in winter, smoothing out what would otherwise be sharper day-night and seasonal swings. Without that buffering, the differences between noon and midnight, or July and January, would be far more severe. Perhaps the most famous quirk is that water expands as it freezes. Most materials get denser as they cool. Water does too, until about 4 degrees Celsius. Then, nearing the freezing point, it begins to expand. Ice floats. That single property changes everything. Lakes and seas freeze from the top down, forming an insulating lid that protects the liquid beneath. Life carries on under the ice. Ecosystems survive the cold. And when spring returns, the melting ice doesn't sink and churn the depths into chaos. Then there's water as a solvent. It's often called universal because it dissolves more substances than nearly any other liquid. That lets it ferry minerals, nutrients, and gases through soil and streams and tissues. Inside organisms, water shuttles materials in and out of cells, carries signals, regulates temperature, and helps maintain structure. Its polarity, one side slightly positive, the other slightly negative, lets it form hydrogen bonds. Those bonds influence how proteins fold, how DNA keeps its double helix, and how enzymes do their work. None of these tricks are arbitrary. They arise from the molecule's shape, the angle between its atoms, the way electrons are arranged, and the nature of its bonds. Change those details and water behaves differently, likely with less flexibility and less support for life. What complicates the picture is that water itself is common in the universe. Hydrogen and oxygen are abundant. We see water as ice on moons and asteroids, as vapor in comets, and possibly as liquid tucked beneath alien surfaces. What seems rare is Earth's bounty of stable surface water. Oceans cover roughly 70% of our world, and they've endured for billions of years. Nothing else in our solar system matches it. Mars holds ice, and probably had streams and lakes long ago, now gone from the surface. Venus may once have had seas, but a suffocating atmosphere boiled them off. Earth kept its water, neither freezing solid nor vanishing to the sky, by staying inside a narrow temperature range for a very long time. How all that water arrived remains an open question. Some of it may have been bound in the rocks that formed Earth, released gradually through volcanic outgassing. Some likely came later, delivered by icy comets and water-rich asteroids. The answer may be both. Either way, the amounts and distribution ended up being just right to fill basins, drive weather, and run a global hydrological cycle. Evaporation, condensation, precipitation, and runoff, continuously moving between land, air, and sea. That cycle underwrites life in every direction. It feeds forests, fills rivers, sculpts shorelines, and lowers mountains grain by grain. It weathers rock into fertile soil and ferries nutrients from one place to another. Without it, Earth wouldn't be the restless, green, living planet we know. Landscapes would parch, plants would fail, food webs would unravel. Water isn't merely an ingredient of life. It's the medium life moves through. Even water's relationship with light matters. It's transparent to visible wavelengths, letting sunshine penetrate the upper ocean and power photosynthesis. If water were opaque, life beneath the surface would be cloaked in darkness. Instead, water emits light, but not all of it. It filters damaging ultraviolet while passing enough energy for life to thrive. Rain, snow, fog, clouds, all parts of water's constant motion shape temperature, visibility, behavior, and mood. They steer migrations, govern planting and harvest, and redraw contours on the land. Their timing. How often it rains, how long snow lingers, when dry seasons start, depends on geography, air currents, and planetary tilt. Earth's climate and its waters are locked in feedback that, for now, sustains a wide variety of life. Even where sunlight never reaches, water carries life along. At hydrothermal vents in the deep, heat and minerals spill from the crust and entire communities gather. Bacteria turn chemical gradients into food, supporting worms, crustaceans, fish creatures found nowhere else. These places remind us that while life can forego light, it still needs water. It's striking that Earth's most common liquid is also its most vital, that a molecule so simple yields function so rich, and that the conditions to keep it flowing, air pressure, surface temperature, planetary mass, are tightly interwoven. This doesn't prove water was engineered for life. It may be that life adapted to water's existing habits. But even that raises a question. Why does water have these habits at all? Why does a 3-atom molecule become the basis of a system that supports such a vast, varied web of living things? In a different universe with different rules, water might not exist. Or it might act differently. Or it might not matter, replaced by some other medium. But in this universe, with these laws, and on this world, water fits the role almost perfectly. It flows, carries, dissolves, freezes, and transforms, quietly running the background processes on which life depends, moment by moment. Look closely at the shapes life takes, the way branches fork, shells curl, petals arrange, crystals grow, and patterns begin to stand out. Not just resemblance, but recurrence. Certain structures show up again and again, across different sizes and settings. Some are symmetrical, some spiral, some follow ratios you can write down with simple numbers. Physical processes can explain them, but the consistency is hard to ignore. Symmetry is the easiest to spot. Faces, bodies, leaves, insects, snowflakes. When the halves of something mirror each other, vertically, horizontally, or around a center, we call it symmetrical. That balance often has a job to do. It can help creatures move efficiently or distribute weight evenly. But symmetry also speaks to perception. Human minds detect it quickly. We tend to find symmetrical faces more attractive. We lean on symmetry in architecture, design, and symbols. It registers as orderly, familiar, complete. In the wild, symmetry frequently carries function. Butterfly wings match because they develop together. A starfish's radial symmetry suits its movement and sensing. Leaves pair off to catch light evenly. Even many viruses assemble symmetrical protein shells, not for beauty's sake, but because symmetry is efficient. One set of instructions used repeatedly. In material terms, it's a shortcut: craft one piece and copy it. Of course, not everything mirrors. Spirals are among nature's most compelling forms. You see them in snail shells and hurricanes, whirlpools and galaxies, pine cones and sunflowers, fingerprints and horns. Spirals tend to appear where growth is ongoing. They allow expansion while keeping form compact. As an organism adds new layers, scales, seeds, petals, the spiral makes room without disturbing what's already there. Many of these spirals align with the Fibonacci sequence, a series where each number is the sum of the two before it. 0, 1, 1, 2, 3, 5, 8, 13, and onward. You see it in petal counts, branching patterns, seed packing. Ratios of successive Fibonacci numbers approach the golden ratio, a proportion that recurs in both nature and art. It's not everywhere, but it's common enough to deserve attention. These forms don't require intent to arise. They can emerge from simple rules of growth and competition. A plant trying to minimize one leaf shading another may evolve a spiral phyllotaxis. That arrangement tracks the golden angle, a fraction of a rotation that spaces elements efficiently. No one designed it for beauty. It simply works and ends up beautiful anyway. This is where the idea of sacred geometry sometimes enters, used variously as spiritual, symbolic, or poetic shorthand for structures that feel meaningful because of their form. Circles, triangles, spirals, hexagons. They appear in religious art, ancient buildings, mandalas, monuments, and in snowflakes, honeycombs, coral. The overlap between nature's geometry and human expression isn't coincidence. We may be copying what we see, echoing familiar shapes in our structures and symbols. Or perhaps we're wired to notice them, to feel certain forms are more complete, more resonant, because they follow rules our brains can sense even if we can't name them. Hexagons are a clear case. Bees build with them because hexagons tile a plane into equal areas using minimal material, a strong, stable lattice with the least wax. But hexagons also appear in cooling basalt, like the Giant's Causeway, and in foams as bubbles settle. The same geometry emerges from pressure and physics without any bees at all. Crystals tell a similar story. Their atoms lock into repeating lattices that can grow into cubes, prisms, and elaborate dendrites. No sculptor is involved. The shape follows internal rules: temperature, pressure, bond angles, and the result feels at once accidental and purposeful. Then there are fractals patterns that repeat at different scales. Tree limbs splitting into smaller twigs, rivers dividing into tributaries, lightning branching, veins spreading, lungs ramifying. Each level looks like a smaller echo of the whole. Fractals excel at distribution. They move energy, air, or nutrients to many points with minimal material, and they often spring from applying simple rules again and again. That's part of the draw. These patterns don't need complexity to appear. They arise from feedback, constraints, and repetition. They're built into how substances behave under certain conditions. And while they aren't the product of intention, they look intentional. They generate a kind of visual logic, too consistent to feel arbitrary. There's also the sense of harmony branches filling space without overlap, spirals pecking seeds without gaps, snowflakes growing along matched axes. These aren't messy outcomes. They're structured. Stack enough structured outcomes and you start to wonder if structure itself is part of the deeper story. Some scientists suggest that certain forms, spheres, spirals, hexagons, are preferred solutions in physical systems. Given enough time and freedom, matter tends towards shapes that are stable or efficient. That's a helpful explanation. But it still leaves you asking, why are the stable, efficient answers the same ones we see everywhere? Why do they happen to support life? Why do they appear in both cells and stars? There's no need to inject mysticism to notice the patterns, but it's fair to ask why the universe's rules produce results that feel both functional and aesthetically consistent. Why forms that help plants grow also align with our sense of art. Why the most effective structures recur most frequently. This doesn't scream blueprint in the literal sense. No drawn plan, no design memo. It does, however, hint at a framework. A set of principles guiding what's possible, what's likely, what can last. Whether that framework comes purely from physics, from mathematics, or from something more abstract, it's baked into how matter organizes itself, and it helps explain why the living world feels so deeply interconnected. If the outer shapes of life impress you with how well they fit, the view inside the cell, the nucleus, the molecular machinery only, sharpens that feeling. The sense of fit doesn't fade under the microscope. It intensifies. Biological systems are precise, layered, and interlocked. They don't merely run, they coordinate. The deeper you look, the more it feels like something beyond bare chemistry still chemistry, but arranged with startling effectiveness. At the center of this is DNA deoxyribonucleic acid, the storage medium for genetic information. Every known organism uses DNA, or its close relative RNA, to carry instructions for building and maintaining itself. DNA isn't just stuff, it's code. 4 bases adenine, thymine, cytosine, guanine form sequences that specify how to make proteins. Those proteins, in turn, run life's operations. The comparison to language isn't just a metaphor of convenience. There's a limited alphabet, there is structure and syntax, and there is meaning. Change a sequence and you can change a protein's shape and function, sometimes a little, sometimes a lot. The same gene can show up across species, doing similar jobs with modest tweaks. And the way this information is read, copied, edited, and interpreted is so organized that it feels less like simple reactions and more like a process. It isn't only storage, it's management. Signals act like start and stop marks, promoters, and terminators, indicating when a gene should switch on or off. Regulatory genes oversee other genes. Repair systems patrol for copying errors and fix them. All of this unfolds within a space just micrometers across in every cell of every living thing. That degree of order raises questions not because we can't imagine a path to it, but because of how astonishingly well it works. The standard account is evolution by natural selection. Small genetic changes create variation. Variants that aid survival and reproduction become more common. Over time, complexity accumulates. Evidence for this is strong in fossils, in lab studies, and in the shared genetics of related species. Even so, the mechanisms themselves are striking. Proteins fold into exact three-dimensional shapes driven by interactions among their amino acids. That shape is crucial. Misfold a protein, and it often fails. Yet in living cells, folding happens spontaneously, guided by the sequence and aided by chaperone molecules that help shepherd the process. no awareness is involved, but the result has an elegance that's hard to overlook. This isn't random thrashing. It's countless parts acting in the right sequence, at the right place, at the right time. Consider enzymes, the catalysts of life. Without them, most vital reactions would proceed far too slowly. With them, rates can jump by factors of millions. Enzymes are remarkably specific. Each one binds its target like a key slipping into a particular lock. They're not just effective, they're selective. Life relies on that selectivity to decide when and how things happen. Then there are molecular motors, protein machines that haul cargo along cellular tracks, spin to power flows, pump ions, or open and close gates. They transform chemical energy into motion in ways that echo familiar mechanics at tiny scales. These aren't exclusive to complex life. Bacteria have them. Plants have them. The toolkit is universal, the parts varied, but the principles shared. That consistency hints at a common origin supporting evolution, while also prompting the question of how the first usable instructions assembled. Where did the initial sequences come from? The first stable proteins? The first membranes that enclosed and separated? Abiogenesis? The emergence of life from non-living ingredients is an active field. Hypotheses abound. Mineral clay templates, deep-sea vent chemistry, ice-shielded microenvironments. There's progress, but no single settled path. The hurdle is that life requires more than molecules. It needs systems that copy, regulate, respond, and evolve. It's plausible that such systems emerged gradually, but the transition from mere chemistry to organized biology remains one of the naughtiest steps to model. That gap between random molecules and working cells is where some observers begin to wonder if biology bears traces of engineering. Not engineering as in human-made machines, but in the sense that the pieces seem exceptionally well matched to their tasks. The code isn't just data, it's executable. It runs instructions, edits itself, responds in real time. Even the compression of genetic information shows this efficiency. Stretch out the DNA in a single human cell, and you'd get about 2 meters of thread. Yet it fits into a microscopic nucleus, wrapped around proteins, coiled into loops, arranged so that the right genes are accessible at the right moments. That isn't chaos. That's organization. And there's more than code and storage. Cells contain rings of feedback signals that cue growth, division, repair, or program death. These controls keep organisms in balance. They react to injury, stress, hunger, infection. Cells talk through chemical messages, adjusting to circumstances. Errors happen, of course. Systems fail. But biology doesn't demand perfection. It leans on resilience. Life is not flawless. Mutations can harm. Breakdowns occur. Yet the persistence of life, in spite of constant disturbance, is itself a kind of engineering adaptive rather than rigid, dynamic rather than brittle. None of this requires a conscious designer. It may be that what we observe are the systems that survived, because they worked, natural selection filtering for function over deep time. That's entirely plausible. Still, when you watch how well everything coordinates, the analogies that come to mind aren't just factory or city or machine. They are software metaphors. A code base that not only compiles, but maintains itself and pushes updates on the fly. Like software, biology stacks in layers. There's the raw code, the DNA sequence. There's the operating layer, the cellular machinery that interprets it. There are inputs and outputs, error checking and feedback. Then there are networks, interactions among genes, proteins, cells, and organs, giving rise to behaviors, responses, even thoughts. So the question shifts. Maybe it isn't, was biology engineered? But can we think about engineering and biology in the same terms? Is the comparison just a helpful metaphor? Or does life's structure hint at a deeper kinship between systems that emerge and systems that are designed? That remains open. But the deeper we read into life's code, the more structured it appears. Not haphazard, not ad-libbed, but layered, regulated, and deeply interwoven. Once you grasp that DNA functions as a code, it becomes difficult not to view it as a kind of language. It doesn't use words or grammar the way speech does, but it has rules, an alphabet, syntax, structure, and meaning. It's written in a 4-letter chemical script, and it carries instructions not only for building proteins, but for when, where, and how those proteins should be made. It's information-embodied directions embedded in matter. The open question is whether that language was invented, discovered, or something that sits between those poles. DNA isn't merely a long chemical chain. It's organized into genes, segments, that can be transcribed and translated into proteins. But genes are only part of the picture. There are regulatory stretches, sequences that tell the cell when to begin or end reading, how much product to make, and under what circumstances to switch state. Enhancers and silencers exert influence from afar. Intron segments spliced out before the final product shape what ultimately gets expressed. And vast non-coding regions once labeled junk, a term now waning help arrange the genome, tune expression, and scaffold the system. All of this behaves less like raw binary and more like a programming language, one with context, layers, and conditionals. In computers, code is compiled and executed. In cells, DNA is transcribed and translated. Both require an interpreter familiar with a symbolic system. Both depend on precision, architecture, and timing. Both fail when the rules are violated. And DNA isn't read en masse. Only a fraction is active at any moment. Different genes switch on in different cell types, at different stages, in response to different signals. The very same sequence can yield different outcomes depending on tissue or environment. That flexibility is part of what makes complexity possible and part of why DNA feels like more than a data dump. It behaves like a system. What's striking is how universal that system appears. All known life on Earth uses the same basic genetic code, the same 4 letters, the same triplet scheme, the same translation logic. A codon 3 bases maps to a single amino acid. There are 64 possible codons and 20 standard amino acids, so the code has redundancy. Some codons are synonyms. Others act like punctuation: start here, stop there. Bacteria, plants, animals all share this framework. That points to a common origin, a moment deep in the past when life converged on one code and carried it forward. But it also prompts the question: why this code? Why this mapping? Researchers have probed whether the code is optimized, whether its arrangement minimizes harmful errors and supports flexibility. Some analyses suggest it's near optimal, not perfect, but surprisingly effective at buffering mutations and preserving function. If so, life may not have adopted just any mapping, but one that performs unusually well. Whether that implies natural selection among codes, or simply that certain structures are more survivable, depends on your angle. Either way, the result is a system that spans all life and has persisted with variations for billions of years. Then there's interpretation. We didn't invent DNA, but we learned to read it to translate chemistry into information. And what we found wasn't only complexity. It was logic. Not just molecules, but instructions. That realization launched entire disciplines: genetics, molecular biology, bioinformatics. With tools like CRISPR, we now edit genes with growing precision. We can synthesize sequences, place them into cells, and watch them run. In a limited sense, we've begun to write in the language of life. But the language itself pre-existed us. That's where design often re-enters. Not because DNA looks manufactured like a microchip, but because it behaves purposefully. It handles information in ways that resemble software, logic, and planned routines. It isn't random static. It's structured input with outputs, woven into every living thing. Meaning complicates the analogy. In human language, meaning is intentional, someone aims to convey. In DNA, meaning is functional. A sequence means something because it causes something. It builds a protein, triggers a process, starts a cascade. Is functional meaning enough to call it language? Or is that just a helpful metaphor? The ambiguity is part of the draw. You can view DNA as the product of evolutionary trial, with workable sequences retained and refined. Or you can see a system so tightly tuned that it hints, not necessarily at a conscious designer, but at a deeper architecture underlying how life organizes itself. Scientists even test wholly new codes, alternative base pairs, synthetic amino acids, altered translation rules. These experiments show that other systems could operate in principle. That only underscores how remarkable the natural code is. Efficient, resilient, and capable of supporting an enormous range of outcomes, all from the same core script. So was DNA discovered or designed? It wasn't designed by us, and it wasn't discovered like an eternal theorem. It looks like a structure arising naturally from chemistry and evolutionary dynamics. Yet the fact that it works so well, so consistently, gives it traits we usually associate with engineered systems. That doesn't resolve anything, but it shifts the focus. From only asking how life began to noticing that life behaves as if it rests on a deep grammar. One we didn't author, and one we're still learning to read. Life, at any scale, needs a boundary or protective interface that separates inside from outside, physically and chemically. For a cell, that's the membrane. For a planet, it's the atmosphere. Unlike a rigid container, Earth's atmosphere is dynamic. It moves, adapts, changes, and regulates. It's not alive, but it acts in concert with living systems. It holds enough in and lets enough out. The air is mostly nitrogen, about 78%, with oxygen next, then argon, carbon dioxide, and traces of other gases. The mix looks ordinary. It isn't. Shift the ratios and the system falters. Too much oxygen and wildfires rage uncontrollably. Too little and animals suffocate. Without nitrogen, plants starve. Without carbon dioxide, photosynthesis ceases. These percentages aren't symbolic. They're functional. They sustain the chemistry life relies on. That balance wasn't instant. Early Earth's skies were thick with volcanic gases, methane, carbon dioxide, sulfur compounds. Toxic by modern standards, but not empty of life. Microbes evolved within it, and some eventually released oxygen through photosynthesis. Oxygen reacted with dissolved iron, forming rust that settled to the seafloor. For ages, oxygen remained scarce. Then it rose, slowly, then sharply. The great oxygenation event remade the air. Oxygen enabled more efficient cellular energy, opening the way to multicellular life. But it also caused die-offs. Organisms adapted to the old regime couldn't cope with the new. The system reset. Life evolved again under new rules. Even now, oxygen levels are not managed by a machine, but by feedback among ecosystems, geology, and climate. Plants and algae produce it. Animals consume it. Fires draw it down. Weathering locks carbon in rocks. Volcanism returns it. When one side wanders, others respond. The outcome isn't perfect stability, but bounded, breathing variation cycles, pulses, feedback. Atmospheric pressure is another quiet cornerstone. At sea level, it weighs in around 14.7 pounds per square inch. That pressure helps keep water liquid, enables efficient gas exchange in lungs, and governs everything from boiling points to tissue integrity. Too low, and water would evaporate too readily. Too high, and respiration would change fundamentally. Pressure sustains the conditions for life, and life helps maintain the gases that set that pressure. Composition also controls heat flow. Certain gases absorb and re-emit infrared energy greenhouse gases like carbon dioxide, methane, and water vapor. Without them, Earth would be a frozen desert. With too many, it overheats. The system breathes. Greenhouse gases ebb and flow, but so far mostly within life's adaptive range. Higher up lies the ozone layer, a thin shield that soaks up ultraviolet radiation. UV damages DNA. Without ozone, mutations spike, cells die, and life struggles. With enough, harmful rays are blunted while useful light passes. Ozone forms through natural reactions among oxygen and sunlight, but it's vulnerable to human-made chemicals. That fragility isn't a flaw. It signals a sensitive system, tuned to specific interactions and reliant on steady energy and chemistry. The atmosphere is in motion. Winds move heat, moisture, and particles around the globe. Jet streams steer weather. Ocean currents couple with air currents. Together they ferry energy from equator to poles, tempering extremes and shaping climate zones. Without that circulation, the tropics would scorch and the poles would lock in ice. With it, broad swaths of the planet remain habitable. Water cycles ride this engine: evaporation, condensation, precipitation. Vapor rises, clouds form, rain and snow return. Rivers run, aquifers recharge, forests grow. The air is the conveyor linking land, sea, and sky. Not as poetry, but as chemistry. No central controller is needed. The system works because temperature, pressure, altitude, and sunlight interact. Still, the outcome looks coordinated. Airflow also carries the small stuff: dust, pollen, microbes. Some particles seed clouds, some ship nutrients across oceans, some start ecosystems in new places. These aren't mere byproducts, they're pathways. They let the biosphere move, adapt, and expand. And through it all, the atmosphere remains just thick enough to count. It stretches roughly 100 kilometers, but most of its mass hugs the first 10 to 15. That slim belt holds every breath, every visible cloud, every audible sound. Beyond, space gradually begins. No hard edge, just thinning to nothing. That thinness makes the air fragile and functional. It admits sunlight. It vents heat. It holds just enough. That same envelope enables flight. Birds and insects find lift. So do planes. Seeds and spores hitch rides. The atmosphere isn't only a shield. It's a medium space for motion. And yet it rarely draws attention. Each breath is planetary. Oxygen that might have been made by a rainforest tree or a microscopic alga. The air around you is not empty. It's the product of billions of years of feedback, adaptation, chemistry, and motion. Not conscious, but structured. Not drift, but cycles. Not stasis, but equilibrium. The kind of regulation that hints at a system with constraints, thresholds, memory. Even if the ingredients are right, even if the chemistry cooperates, timing still matters. Not just minutes and hours, but seasons, cycles, ages. On Earth, things don't simply happen. They happen to a beat. Some rhythms are quick, some slow, some measured in the patient ticks of geological time. Nothing about these cycles is mechanical in the sense of a clock's springs, yet they keep time just the same. Not built, but real. And that timing is what keeps everything working. Earth turns once every 24 hours. That rotation gives us day and night and sets the tempo for sleep, activity, and photosynthesis. From insects to trees to people, living things carry internal mechanisms that synchronize to that pattern. Circadian rhythms, hormone cycles, feeding and flowering times. These aren't only reactions to light, they are programs shaped by eons of repetition. The planet spins and life spins with it. The year has its cadence too. One trip around the sun takes about 365.25 days. Combine that motion with Earth's axial tilt, and you get the seasons. They're not cosmetic. They steer migrations, cue breeding, regulate growth. Bears sleep, birds travel, crops ripen. Even microorganisms time behavior to seasonal signals. That level of coordination would be impossible without reliable orbital timing. Earth's path is notably steady. Our orbit is almost circular, just eccentric enough to vary sunlight without driving extremes. Some worlds trace more elongated paths, delivering blistering summers and bitter winters. Earth's near constant distance keeps solar input within a range that supports life year-round, even as the seasons turn. But the planet's motion includes more than spin in orbit. There's precession, a slow wobble of the axis-like, a top that takes roughly 26,000 years. There are shifts in obliquity, the tilt itself, and long-term changes in orbital eccentricity. Together these are called Milankovitch cycles, and they influence climate on grand scales, ice ages waxing and waning, glaciers advancing and retreating, rain belts sliding across continents. The timing isn't exact, it's probabilistic, but it's regular enough to leave its mark on history. The moon plays along. Its orbit governs tides, of course, but it also lengthens the day. Over billions of years, the moon's pull has been slowing Earth's rotation. Today grows by milliseconds per century. Too small to feel, but cumulative. A billion years ago, daytime lasted closer to 18 hours. That matters. It affects how long organisms can photosynthesize, how internal clocks align, how heat accumulates and disperses. Evolution didn't occur in a fixed frame. It adapted to a moving one. Other cycles run beside these. The sun's activity swells and dips on an 11-year rhythm, with sunspots and radiation rising and falling. That activity tickles Earth's magnetic field, disrupts satellites, and may fold subtly into climate. Geological cycles take longer still. The drift of plates, the opening and closing of ocean basins, the birth and burial of mountain ranges. Even mass extinctions seem to cluster in patterns, though the causes remain debated. Inside cells, clocks tick too. Molecular timers measure time with proteins that rise and fall in looping feedback. These aren't mere reactions. They anticipate. Cells don't just respond to light, they expect it. Genes switch on and off at set times. Repair crews mobilize when damage is most likely. Behavior is not only reactive, it's scheduled. In humans, internal clocks govern sleep, body temperature, hormone pulses, digestion. Jet lag is what happens when internal time falls out of sync with external time. Health frays when rhythms are chronically disrupted. The body needs consistency, not rigidity, but pattern, and Earth's motion provides it. Reproduction rites, cycles as well menstrual periods, gestation lengths, mating seasons, tied directly or indirectly to light and time. Some links are obvious, others lie buried in evolutionary memory, leftovers from ancient timing schemes that no longer serve a clear purpose but still tick away. And beyond biology, there is cultural time. Humans invented calendars to track sun and moon. Farming depends on planting and harvest at the right moments. Rituals align with solstices, equinoxes, lunar phases. Our seconds, hours, and years are all miniatures of planetary motion. We wear watches, but they are just compact echoes of cosmic rhythms. None of this implies control. Earth doesn't know it's turning. The sun doesn't keep count. The moon doesn't tally tides. But the outcomes look like rhythm because they persist long enough for life to notice. And once life noticed, it folded those rhythms into itself. What stands out is how these cycles layer. Fast one's day and night rest on slower one's seasons, years, orbital variations, and those rest on deeper cycles still. Wandering continents, rising mountain chains, aging stars. Each layer nudges the next. Together they form a scaffold not imposed from above, but born of interaction, motion, and inertia. That scaffold opens windows of possibility. Sometimes conditions line up, warmth, light, moisture, stability, and new forms emerge. Other times, it tightens. Ice, drought, competition, and life adapts under pressure. Either way, adaptation needs time. Earth's regularity grants it. Predictability isn't the same as purpose. A clock keeping time doesn't require an observer. It just allows one. Earth, as it happens, is buildable. Life, weather, chemistry, culture, all stack atop consistent timing. None of it works if the pace drifts too far. Some parts of biology feel like they arrived one small improvement at a time. You can trace them, minor changes, modest advantages, slow shifts over generations. Others seem to leap, not because they defy explanation, but because they work so well, it's hard to picture a partial version. The human eye is one of those. It's a system with many pieces, each leaning on the others. Light passes through the clear cornea. The iris tunes brightness. The lens focuses. The retina turns photons into electrical signals. Those signals flow along the optic nerve to the brain, where an image is built, not passively received, but actively interpreted. Every second, your eyes deliver a flood of input, and the brain sorts it into motion, color, contrast, distance, threat, comfort. More than a sensor, the eye is a dynamic optical device. The lens reshapes for near and far. Pupils widen and shrink with light and with emotion. Tiny muscles track targets, stabilize the view, and coordinate with head and body. The eye isn't alone. It plugs into a system built for coordination and prediction, and it isn't just the hardware. The brain layers on processing edge detection, color correction, pattern spotting. It fills blind spots. It stabilizes a scene even while you move. It interprets based on memory, expectation, and context. Vision is not a recording. It's an interaction. The usual explanation is evolutionary. Eyes grew from light-sensitive patches on early organisms. Over time, dimples became deeper, lenses formed, muscles added control, focus sharpened. You can still find nearly every step of this ladder in nature. From simple photoreceptors in jellyfish to compound eyes in insects to the sophisticated vertebrate eye. Each increment confers an advantage even before the system is complete. That account holds up. What stands out is how far vision has gone, not just in humans. Raptors perceive ultraviolet and pick out motion at staggering distances. Certain shrimp detect polarized light and colors beyond our imagination. Cats and owls operate in near darkness. Squid and octopuses evolved camera-like eyes through a different route, yet reached comparable performance. These aren't approximations. They're tuned instruments. Fast, responsive, high resolution. And vision is only one sense. Bats and dolphins use echolocation, emitting high-frequency pulses and reading the returning echoes to map three-dimensional space in milliseconds through air and water. Electric fish project weak fields to sense shapes in murky rivers. Some insects see ultraviolet or infrared. Some snakes detect heat from warm bodies. These systems don't just detect, they compute. They extract structure out of noise in real time. Even something as familiar as the human hand is an engineering masterpiece. Bones, tendons, muscles, nerves, finely coordinated for delicate motion. The opposable thumb enables grip and manipulation. Fingertips resolve textures at astonishingly small scales. Vision and touch sync to deliver precision that machines still struggle to match. Playing an instrument, typing, tying a knot. Movements that are timed, tuned, and continuously corrected. Parts of us rebuild. Skin heals, bones knit, the leva regrows. Other tissues don't replace themselves as readily, neurons, for instance, but even there, the system flexes. The brain rewires, forms new pathways, compensates for loss. There's adaptability built in. Not infinite, but enough to endure. Then there's development. Every human begins as a single cell. That cell divides, differentiates, and organizes into tissues, organs, systems. The instructions are encoded in DNA, but the execution is spatial, continuous, responsive. Cells signal and coordinate. They read gradients, sense contact, and respond. We aren't assembled like a machine. We grow from simple to complex while checking, adjusting, and regulating along the way. Much of this is timed down to hours when organs form, when systems connect, when transitions must occur. If the timing slips, development can fail. Most of the time, it doesn't. It proceeds with an accuracy that rivals engineered systems. That accuracy isn't perfection, but it's enough to let complexity arise again and again. You can find the same precision in systems we rarely notice. The immune system identifies and neutralizes threats using memory and pattern recognition. The endocrine system tunes energy, growth, stress response, and reproduction. The cardiovascular system delivers oxygen and nutrients with striking efficiency, adjusting flow on the fly in response to movement, temperature, and damage. All three run on cells, self-contained compartments with their own logistics, membranes, organelles, transport channels, waste removal. Each cell follows instructions, responds to signals, adapts, and repeats the cycle, dividing, dying, renewing. No single feature settles any debates. And yet, when you stack the systems, vision, motion, balance, coordination, communication, you don't just get survival. You get capability, awareness, creativity, the capacity to meet the world with detailed, responsive action. From the outside, humans can seem fragile, soft, slow, tool-dependent. But biologically, the human body is both adaptable and precise. It can run distance, heal from injury, acquire language, manage tools, raise young, link memory to planning, and balance emotion with reason. These aren't afterthoughts. They're central to how we operate. None of this cuts against natural processes. Evolution is a clear mechanism, variation, selection, adaptation. But even within that frame, some traits seem unusually expansive-tuned, not only for function but for range. The eye doesn't merely see. It adjusts to darkness and glare, tracks motion, and focuses near and far. The ear doesn't only hear, it discerns pitch, direction, and rhythm. The body doesn't just move. It climbs, swims, dances, and writes. These aren't lucky one-offs. They are systems layered on systems, refined over time, interacting across scales. There's no need to call them intentional. Still, they work with a completeness that draws attention, which leads to a larger question less about the pieces, more about their interplay, integration, coordination. What keeps these processes in sync? What enables them to respond coherently to a world that never stops changing? Some things happen because they must. Gravity pulls, water runs downhill, iron rusts. Regular, predictable, mechanical. Other events are not like that. They're contingent and singular. An asteroid arrives. A molecule mutates. A volcano erupts. We call them accidents. Not errors, but outcomes that could have gone another way. What's striking is how often such accidents, in hindsight, seem to steer things toward coherent ends. Take the asteroid that struck Earth about 66 million years ago. It slammed into what's now the Yucatan Peninsula, releasing more energy than 1 billion nuclear detonations. Rock vaporized. Firestorms circled the globe. The sky went dark. Food webs collapsed. The age of dinosaurs ended. That wasn't slow evolution. It was a rapid reset, violent and total. Yet it opened ecological space. Mammals expanded, diversified, and eventually took the lead. Without that single strike, humans might never have arrived. There are other inflection points. Around 2.5 billion years ago, Earth's atmosphere began filling with oxygen not due to catastrophe, but because single-celled organisms learn to use sunlight to split water. Photosynthesis. The exhaust was oxygen, which accumulated in the air and oceans. At first, it poisoned existing life. Over time, it enabled new metabolisms with higher energy yields, paving the way for complex cells and eventually, multi-celled organisms. One biochemical breakthrough changed the planet's trajectory, not by intention, but by consequence. Roughly 600 million years ago, complexity accelerated. Nervous systems, eyes, skeletons. An explosion of forms appears in the Cambrian fossil record. Oxygen may have crossed a key threshold. Genetic innovations like regulatory genes that define body plans likely played a role. Whatever the mix, the timing was tight. Shift the window by a few million years either way, and the environment might not have supported the surge. Even the slow rearrangement of continents reshapes life in outsized ways. Plate drift over millions of years changes ocean currents, isolates populations, opens migration corridors, and shuts others. Mountain ranges rise to redirect rainfall. Species are brought together or pushed apart. Those motions set the stage for selection. Who survives, who mingles, who disappears. The moon's birth, probably from a rare, high-energy impact with a Mars-sized body, is another example. Chaotic and violent, yet the outcome was a large, stable satellite that helps steady Earth's tilt, tides, and rotation. Without it, climate might swing too erratically for large ecosystems to hold. None of these events were scheduled. They weren't guaranteed. Yet their consequences reached far beyond their immediate blast zones, not merely chains of cause and effect, but crossroads moments after which the set of possibilities changed. Biology is full of such turns. The rise of DNA as stable information storage, proteins with versatile functions, the emergence of eukaryotic cells with internal compartments like nuclei and mitochondria. That last step likely began when one cell engulfed another, not as a meal, but as a partner, a merger that became permanent. Symbiosis enabled larger, more complex forms. Sexual reproduction, mixed genes, boosting variation, and speeding evolution, but at the price of requiring partners. And what about consciousness, not just behavior, but awareness, memory, planning, reflection? Not inevitable, not universal, but real and linked to a web of prior developments, any one of which could have gone another way. The human brain with its layered functions, from movement and pattern recognition to language, rests on a long biological history that began with simple reactions to light and touch. Each rung relied on earlier one's neurons, then circuits, then coordination across regions. And at every stage, conditions had to line up: energy supply, protection, time to grow. One way to view this is as a filter. Many planets may exist, many may offer water, warmth, or the right chemistry. But to reach complexity, then consciousness, then civilization, a long series of alignments is needed, not just any order, but the right sequence, at the right intervals. Too soon, and systems fail. Too late, and windows close. That doesn't imply a plan. It does suggest rarity. What's unsettling is how narrow some thresholds are. A little closer to the sun, and oceans might have boiled. A little farther, and they might have frozen. If gravity were weaker, the air might drift away, stronger, and the planet could collapse into something unlivable. If water's properties were different, even slightly cells might not hold together. If DNA couldn't fold as it does, replication would be unreliable. If that asteroid had arrived 30 seconds earlier or later, the extinction pattern might have changed. When things work, dependencies fade into the background. Pull them out and study them, and the scaffolding comes into view. So much had to happen just to make this version possible. Not perfect, but stable. Not ideal, but viable. People often say fine-tuning, a word that implies intent. What we can point to directly is precision, a convergence of variables that fits unusually well. not because each element is extraordinary, but because their relationships, timing, chemistry, physics, events stack in a way that leaves little room for error. And yet the system holds. It changes. It breaks and rebuilds. But it doesn't fall apart. Earth's story is crowded with accidents, extinctions, collisions, reversals, shifts, and somehow those same disruptions often generate new structures, greater diversity, new paths, higher complexity. It's not that accidents are scarce, it's that outcomes keep landing in ranges that allow life to continue, sometimes by a hair's breadth, sometimes astonishingly so. Long before lenses, labs, and datasets, people looked out and asked where the world came from. They watched stars sweep the sky, tracked storms and seasons, birthed and buried their dead, and what they noticed most was regularity, patterns, cycles, things behaving the same way again and again. Confronted with that consistency, the next question was almost inevitable. Who or what made it so? Early answers were personal. Gods, spirits, ancestors, named forces with intentions and stories. In those views, the world wasn't merely a setting, it was a creation. Mountains, rivers, sun and moon, animals and people, all shaped by unseen agents acting on purpose. Sometimes that purpose was kind, sometimes capricious, but either way, it lent events meaning. Drought wasn't only weather, it was a message. Fortune wasn't just luck, it was favor. These ideas weren't random. They were attempts to make sense of something larger than any one life, something lawful, yet responsive. Modern science has replaced many such explanations with models grounded in observation and prediction. But the impulse to look for agency behind structure didn't vanish. It changed shape. In ancient philosophy, order often implied a mind. Some Greek thinkers posited a prime mover. In Eastern traditions, the world is sometimes cast not as a product, but as an unfolding order. Religious texts tell stories in which creation is deliberate, even intimate. Later, with monotheism and formal theology, design took on new language. Creation ex nihilo, purpose, divine will. The cosmos wasn't only shaped, it was chosen with a beginning, a structure, a goal. For centuries, that frame guided not just devotion but investigation. Early naturalists often saw their work as reading the mind of God in nature. Then Darwin offered a model with no foresight required. Evolution by natural selection described how complexity could arise from simple beginnings through variation and filtering over time. It was a major turn not because it disproved design, but because it no longer needed it to explain biological order. That didn't resolve every question, but it shifted the ground. Since then, science has moved further along that path. The standard view holds that systems, biological, planetary, cosmic, can emerge from the interaction of rules, matter, and time, complexity from simplicity, not by top-down construction, but by self-organization. At each step, the process is local. No central controller, just feedback, selection, iteration. Even so, the sense of design lingers, not as a watchmaker in the sky, but in the character of the outcomes. The brain behaves like a computer. The genome behaves like a script. Physical laws behave like an interface. The analogies aren't perfect, but they persist. We keep finding systems that resemble the systems we build. And now, the loop tightens, because we don't just describe biology with engineering terms, we engineer with biology. We write genetic code, we simulate ecosystems, we evolve digital organisms inside algorithms. We build models that design other models. In doing so, we watch the line between natural design and artificial design blur. Artificial intelligence, once speculative, now writes, paints, translates, predicts. It doesn't think like we do, but it processes structure. It finds patterns and sometimes produces answers that surprise even its makers. Algorithms evolve. Neural nets adjust. Complex behavior emerges from simple rules. Sound familiar? This doesn't mean algorithms are divine, but they force a question. Is design always conscious? Does order require a mind or just the right conditions? If a machine can create something useful without understanding it, maybe understanding isn't required for construction. And if nature can create structure without intention, maybe intention isn't the only path to complexity. That's where the conversation sits, not as science versus religion, but as differing models of emergence. Some say the universe is self-organizing. Others say it was shaped. Both agree on this. The outcomes are structured. Structure can be described, analyzed, replicated, sometimes predicted. And it runs deep from physics through chemistry and cells to consciousness. What's changed most is how we talk. We don't lean on built by hands anymore. We talk about systems, constraints, thresholds, probabilities. Yet the core instinct remains. Function implies form, and form implies cause. It crops up in everything from simulation theory to the search for extraterrestrial intelligence. If something works too well, we look for a reason. The scale has widened too. Ancient answers stayed local. Rain, harvest, war. Now the questions stretch outward. Was the universe itself configured for life? Are there versions where life fails? Are we simply the result of random sorting? Or are we in a setup that favors observers because only observers can notice? That idea, the anthropic principle, reframes rather than resolves. In a life-bearing universe, of course, you find yourself able to observe it. But it doesn't explain why such a universe exists at all. So the cycle continues. From gods to algorithms to simulation hypotheses, each iteration returning to a stubborn observation. Outcomes look like they work. Not always gently, not always kindly, but with a level of precision, integration, and timing that resists being waved away. It began as metaphor. The brain as machine. DNA as code. The cell as factory. Those comparisons were never literal, but they gave us Handel's ways to picture the invisible. Over time, the metaphors started to look less like cartoons and more like mirrors. As our digital systems grew complex, they didn't just resemble biology, they began to behave like it. Early simulations were simple. A digital ant following a scent, a flock of virtual birds aligning in flight. But even then, something striking happened. From simple instructions, complex behavior emerged, not because it was scripted, but because conditions allowed it. Interaction gave rise to patterns. That principle now powers everything from game worlds to climate models. We feed data, set constraints, and hit run. The system responds. Sometimes it surprises, sometimes it fails. Often it behaves in ways that feel familiar. Populations wax and wane, settlements form, languages evolve. Artificial agents discover strategies we didn't write, not through understanding, but because the math supports it. Simulations don't conjure real worlds, but they can approximate them. They let us explore counterfactuals, raise the temperature, mutate a gene, deplete a resource. They become more than tools, they're thought experiments that compress possibility. At a certain point, the gap between model and world narrows. You can simulate evolution. Digital organisms with virtual genomes mutate, compete, adapt. They invent gates, sensors, even cooperation. No one tells them how. They discover what works by trial. Because computers don't tire, those cycles run thousands of times faster than nature's evolution in ours. The solutions they find aren't always elegant by human taste, but they're effective. Algorithms seek not beauty, but success under given rules. And often the patterns they rediscover, spirals, branches, cycles, fractals, echo natures, not through copying, but convergence. That echo raises a question. If minimal input systems tend toward familiar forms, what does that say about those forms? Are they merely efficient? Or is there a deeper geometry that all systems, biological or artificial, fall into when given freedom? The simulation idea pushes further. Some suggest our universe might itself be a simulation, not metaphorically, but literally running on an unseen substrate. It isn't sci-fi anymore. It's a philosophical hypothesis entertained by physicists and computer scientists. If some advanced civilization can simulate conscious minds, there might exist far more simulations than base realities. Statistically, we could be inside one. There's no direct evidence. Still, there are curious features, limits that look like resolution, discreteness in matter and energy, measurements that collapse when observed, boundaries that feel more computational than continuous. These might be properties of a physical universe or artifacts of a system with edges, rules, and shortcuts. Even if the simulation hypothesis is false, it's useful. It forces a systems view. If reality behaves like a system, we can study it like one, map its rules, test its parameters, search for consistency. Not assuming purpose, acknowledging structure. Virtual reality adds another turn. We create digital spaces immersive enough that brains begin to treat them as real games, training environments, design tools. Places that don't exist yet still produce meaningful experience. In those worlds, perception is the variable. If the brain accepts it, the line between simulated and real blurs. Inside those same spaces, we set agents learning systems that adapt. They don't think like us, but they process information, weigh options, and exhibit behaviors that look like learning not conscious, but pattern seeking. It isn't hard to imagine a near future where simulations run not only to predict, but to explore, discovering new chemicals, testing medicines, evolving designs, all inside digital frameworks, guided not by handwritten steps, but by training and selection. That's where the boundary phrase between writing a program and raising one, between architecture and emergence. It doesn't erase the old questions. It reframes them. If reality can be simulated in part, the distance between design and discovery narrows. Perhaps design is what happens when conditions favor particular outcomes. Perhaps discovery is recognizing what structure already permits. If something looks structured, it's natural to ask whether it was made that way. The next question is harder. If it were designed then, why like this? If it were designed then, why like this? Because this version of Earth is not pristine. It mostly works. It clearly supports life. But it's also uneven and fragile, full of trade-offs, blind spots, and strange compromises. Bodies wear down. Ecosystems collapse. Disasters kill without warning. The same engines that enable growth also permit suffering. If there's design here, it isn't tidy. Design, as people imagine it, comes with assumptions that things are made for reasons, that there's a best version, that problems are exceptions. Nature doesn't play by those rules. The systems that last aren't the most elegant. They're the ones that survive long enough to matter. Often that means good enough, not ideal stable rather than optimized. Plenty of biology reads like a compromise. Our spine, inherited from four-legged ancestors, strains under upright posture. The eye has a blind spot where the optic nerve exits. Airway and food passage share space, inviting choking. The brain, for all its power, is vulnerable to distortion, addiction, delusion, degeneration. Evolution explains this. Structures adapt by reuse. Solutions get copied and tweaked, not rebuilt from scratch. Reuse brings inefficiencies, overlaps, kludges, vestigial remnants, but it also grants flexibility. A solution that works doesn't have to be optimal. So if there's design, it may not resemble ours. Not pre-planned, not driven by a single objective, more like emergent architecture shaped by constraints, feedback, and accident. In that frame, why like this turns into, why does this version keep surviving? That's a different question. Scale matters too. Some patterns look messy up close, zoom out and rough edges blend into structure. Climate swings but tends to stabilize over long spans. Ecosystems fail, then reform around new players. Genetic diversity opens vulnerabilities and also resilience. Life as a whole has lasted billions of years. That signals durability, not perfection. Still enough to invite wonder and discomfort. Because alongside finely balanced systems are plenty that feel arbitrary. Why lean so much on randomness in reproduction? Why do beneficial mutations take so long to spread? Why do so many creatures live in cycles of competition and scarcity? One answer framed as design would be that suffering isn't a bug, but a feature. Pressure drives adaptation, scarcity drives cooperation, failure drives novelty. But that answer carries weight. It implies a moral distance, a system that works by letting parts of itself break. Humans imagine better worlds, no pain, no aging, no extinction, bodies that fully repair, a planet without tsunamis or drought. If this world was designed, why not like those? Perhaps trade-offs are unavoidable. Perhaps complexity needs risk. Perhaps self-modifying systems can't be tightly constrained without losing the capacity to grow. But those are guesses. They assume goals. The patterns we can see point to survival, not direction. In technology, we design toward explicit end speed, efficiency, safety. Nature doesn't optimize those targets. It adapts under pressure. Some results are elegant, others awkward. Some parts are ancient, others improvised. The brain is powerful and fragile. The immune system is adaptive and overreactive. Intelligence enables planning and anxiety. There's no single theme tying it all together, just a lineage of forms building on what came before, rarely resetting to zero. If design exists in that, it's decentralized, layered, maybe even unconscious. The idea that Earth was designed doesn't require perfection, but a reality packed with beautiful systems that sometimes fail in brutal ways suggests that if design operates here, it follows different rules. Neither human logic nor human goals, perhaps not even human values. It's also possible we're asking the wrong question. Design and randomness aren't strict opposites. Structure can arise without being imposed. Feedback, replication, and memory can yield apparent intention. In that light, why like this becomes less about meaning and more about consequence. Not who chose this, but what made this sustainable. There's a point in every system, no matter how detailed, tested, or well-modeled, where explanation stops. Not because there's nothing left to know, but because our tools hit their limit. When that happens, something else moves in. Sometimes silence, sometimes more questions, sometimes belief. Science works by drawing boundaries. What's measurable, repeatable, observable. It handles what can be tested. Gravity isn't a theory because someone believes it. It's a theory because it predicts what will happen next. Same for thermodynamics, electromagnetism, evolution. Science's strength isn't in what it says about meaning, but in how well it predicts. People, however, don't live on prediction alone. They live on story, purpose, connection. When those aren't in the equations, they show up elsewhere, in frameworks that speak in terms of why rather than how. For some, that's religion. For others, philosophy. For many, a blend shaped by culture, family, language, history. Systems that aim to explain not only how the world works, but what it means. Those systems don't disappear as science advances. They evolve alongside it. Physics at its edges starts to resemble philosophy anyway. Quantum mechanics speaks in probabilities, observation, uncertainty. General relativity reshapes space and time themselves. These ideas aren't intuitive. They stretch language and resist pictures. Yet they're real-tested, technologized, foundational. Even so, the models break down. We don't have a theory that unifies gravity with quantum mechanics. We don't know what dark matter is. We can't say why the constants of nature, like the electron's charge or the strength of the nuclear force, take precisely the values that permit atoms to exist. These aren't small holes. They're fundamental. Into those gaps, people bring meaning. Some say the universe simply is. No deeper reason. No hidden message. A structure that happens to work. A lucky throw that landed livable. Others see intention not necessarily in the details, but in the fact of order. That laws hold, that minds arise, that patterns repeat in ways that allow reflection. Neither stance can be proven, and neither needs to be. They're not scientific models. They're lenses, ways to read what science observes. What's striking is how many questions live in both domains. What is time? What is consciousness? What preceded the beginning? Where does order come from? These aren't inherently spiritual, but they become spiritual when answers turn into values, identity, responsibility, purpose. Even belief in science rests on a kind of trust. Not blind faith, but confidence in method and integrity, in the assumption that reality behaves consistently, that measurements matter, that cause and effect are more than illusion. Not supernatural beliefs, but still foundational. Science doesn't prove itself from the outside. It works because it assumes the world can be known. Faith, in its many forms, works differently. It doesn't require observation. It persists when evidence thins out. It offers story where data stops. That doesn't make it less real, just suited to different questions. For most of history, science and faith weren't separate. Early scientists often worked from religious motivations, seeking the order of creation and nature's laws. Only recently have the two been framed as opposed. In practice, most people live in the overlap, trusting science to explain how, turning elsewhere to ask why. The interesting parts are at the boundaries. When faith makes scientific claims, conflict tends to follow. When it speaks in metaphor, mystery, and meaning, it can fill spaces science doesn't reach. When science speculates about multiverses, simulations, or the nature of consciousness, it begins to sound like belief. That isn't failure. It's boundary testing. A sign that curiosity persists beyond the model. Many physicists acknowledge this openly. They call the laws elegant, surprising, beautiful. They talk about simplicity veiled in chaos, symmetry breaking into complexity. They use fine-tuned, not to imply a tuner, but to mark how narrow the interval is between a sterile universe and a living one. Others look at the same data and see randomness and ocean of outcomes, with this one just happening to work. The anthropic principle? Of course, we observe a life-supporting universe, because only such universes produce observers. Doesn't explain why there is such a universe. It explains why us. Still, the question lingers. Is the precision we see a fact of nature or a mirror of our interpretation? Are we reading meaning into structure or uncovering meaning that's there? That's where belief steps in, not to close the case, but to propose, to imagine, to hold the door open. Not everything needs resolution. Some parts of life go better with questions intact, which brings us close to the end, though not to a verdict. The last question isn't whether Earth was designed or by whom. It's how we live in it now, with the systems we inherited, the air and water, the timing and patterns, the chance to reflect, imagine, and build. The question never really disappears. It softens under routine workdays, city noise, familiar habits, and then flares again. A night sky flung with stars, a delicate fossil in a palm, a perfectly timed event. Up it rises. Did we find all this, or were we meant to find it? Designed or discovered? Built or emerged? Different routes, often the same destination, standing at the edge of what can be explained, looking outward. If Earth is a design, it is the most intricate any mind has encountered. Molecules positioned, cycles tuned, feedbacks layered on feedbacks. A system that sustains itself across billions of years, recycling and reshaping, allowing not only survival but understanding. That would be a kind of miracle not of spectacle, but of quiet structure. If Earth is not a design, if it assembled itself through the slow traffic of physics, chemistry, and time, it is no less astonishing. Because what emerged eventually noticed itself. A planet that became aware. A process that looped back and saw the process. Life that learned to ask. Either way, the outcome is the same. We are here, thinking, watching, wondering, making tools, sense, and stories, studying cells and galaxies and equations, and ourselves. We draw maps not because we're instructed to, but because we need to know where we are. And we are here, not only on a rock that circles a star, but fully present, aware of the conditions that allowed awareness, able to recall what came before, and imagine what could follow. We map not because we're told to, but because we need to know where we are. And we are here, not just physically, not merely on a rock orbiting a star, but fully here, aware of the conditions that permitted awareness, able to reflect on what came before and imagine what might come next. Whatever else that is, it's rare. And maybe that's enough to hold, even if the origin remains unresolved. Maybe the power isn't in knowing the answer. Maybe it's in being able to ask, because the systems continue with or without a final explanation. The rotation of the Earth, the pull of the moon, the breath of the atmosphere, the rise and fall of ecosystems, the ongoing dance of genes, memory, and environment. The rules haven't changed, but now we see them, and seeing them doesn't require certainty. It asks for presence, attention, a willingness to accept that some things are structured and strange and stunning, not because they were made for us, but because we can see them at all. That might be design. That might be chance. Either way, it's discovery. And it's still unfolding. Thank you for spending this time, not rushing, not reaching, just sitting with a question that doesn't need solving to be worth asking. Whether Earth was designed or discovered, whether these systems are intended or emergent, the world is no less astonishing. And you here now, breathing, aware are part of that system too. Sleep well or think long. There's no pressure either way. The planet will keep turning, the patterns will continue, and the good questions will still be here in the morning.